Okay, so today is the last class. I did not know that. So let us take some extra time and finish what we were supposed to finish this week. Uh, so last time we were doing we had this concept that you have seen before, that for a finite group order is defined and then it is between 1 and size of the group. Right, so we gave two proofs. One proof is only for abelian groups because it requires this property x to the n equal to 1, x to the n equal to e. For general groups, you have to come up with this idea of cyclic groups. Any questions till now? Yeah, so we have stated this theorem, we have not proved it, I think, that order of an element divides the order of the group. So we'll prove that today. If we have no questions, then let's start a new subtopic, which is subgroups. Yeah, so you have seen cyclic group, and in fact you have also seen a subgroup which is cyclic, which was basically you take any element x and then you look at all the powers possible. That forms a group, and so it's a subset which has a group structure, we call it a group, subgroup. But there may be more complicated subgroups, so let us define that term. So subset H of a group G is called a subgroup. Subgroup of G, and it is written like this: H less than equal to G. Okay, this will mean that H is a subgroup of the group G if H is not an empty set, it is closed under group operation. So okay, then we need to identify also that operation. So that's G star is closed under star and has inverses. Right, so it is a subset which has elements and they have to be closed under multiplication, which means that the group operation star. So if H1 and H2 are elements, then H1, in fact if H1 is an element, then H1 square is also an element, and H1 cube is also an element, and if H1 H2 are elements, then H1 times H2 and H2 times H1 are also elements. Moreover, H1 inverse exists, or an E exists. Okay, so such subsets are very special, these are called subgroups. This last thing, actually I have written it, but it was not needed because it's implied by the other properties. Okay, E will be in H. Because if you have A and you have A inverse and you have closure, then A times A inverse is an element, so E is an element, right? That's so. But just to be careful, remember that this it will share E with G. Okay, so maybe we can see one example. So in the case of integers, right, integer is group only with respect to plus. What are the non-trivial, or what are the subgroups of this G? So first is that you can take G itself, right? G is a subgroup of G, and 0 is also a subgroup, right? So the identity element, just that is a subgroup, everything is a subgroup. What else? What? 0? Z slash n, you mean? Even, okay, I see. So you mean 2Z? Yes. Yeah, so if you look at even numbers, basically every element you multiply by 2. So that is a proper subset of integers, and that is a subgroup, right? Because even plus even is even. And inverse and 0, everything is there. What else? -1, 0, 1. No, if there is 1, then you will have everything. So that is like G. No, something new is you take a number and its multiples. That also is a subgroup. N equal to 2 is not special, right? So n multiples of m, multiples of a number n are also, they form an additive, so abelian subgroup. And yes, and you have these large scale groups. So Z is a subgroup of rationals, subgroup of reals, subgroup of complex. Right, we have these famous groups, they have this subgroup tower structure. Is that clear? And you can do, so one more interesting example you can see, in integers if you add square root, then with respect to plus, this is a subgroup of reals, right, where this z square root 2 is basically a plus b root 2. Or you can as well take square root of -1. It just has similar property. The property is that you take integer linear combinations of 1 and square root of something. Additively, obviously, it's closed, and also inverse is there, and 0 is there. So that's another subgroup which is of interest. Another interesting subgroup which is important. So till now we have only seen examples of abelian groups and subgroups. So if the group is abelian, what can you say about the subgroups? They will also be, so abelian groups have only abelian subgroups. Maybe we write that. What about the converse of this? So what can you say about non-abelian groups? So non-abelian groups, the subgroups can be abelian or they can be non-abelian, anything is possible. So in that case, there is this interesting object which is you look at those elements that commute with everything. Okay, so look at those H whose multiplication with every element is commutative. So what is this? So this is called the center of G. And its properties are, is it a group? So if H1 commutes with everything and H2 commutes with everything, then you can prove that H1, H2 also commutes with everything. Just a consequence of these two identities. And so it's a group. Is it an abelian group? Okay, so the center is an abelian subgroup, irrespective of what G was. If G was abelian, then what can you say? Then the center is abelian and it's equal. I mean, center is equal. If G is abelian, then everything commutes with everything. So CG is G, and if CG is G, then the group is abelian, right? So that's another way to say that your group is abelian. The center is a subgroup that is abelian. That is everything. CG is equal to G. What else? So one thing you can think about is what are the subgroups of a cyclic group? Okay, so for a cyclic group, like we had this, the group which is generated by powers of x, identify the subgroups of that. So for example, will these subgroups be cyclic or not? They have to be, right? Because if a subgroup H of this G has an element y, then the powers of y are in there, and you can show that nothing else is there, because if something else is there, you can actually look at the power of that and you can argue. So you know that it's a cyclic subgroup, and then you can identify what exactly it is. You can think about that. We don't have time in this class for that. So subgroups have a so remember that from the point of view of computer science, you are studying subgroups to do recursion. A group can be a complicated object, so you will reduce it to a smaller case, and that is a subgroup. So technically what you will do is the following. That if H is a subgroup of G, consider an element here and look at the set H times G, which is product of H with every element. So what do you think this will be? For us, you take a subgroup element and you multiply it with everything. So basically, when G is in H, then HG will also be in the subgroup H. But if G is outside H, then you don't know. Then I mean, it may be also, the product also may be outside H. So basically, G in G in H implies that this product is also in H. But if G is outside H, then the product, you can't say anything. Can you? What can you say if G is not in H? Can small h times G be in H? Right, because if it was some element H prime in big H, then G will be equal to H inverse times H prime, which will again be in big H. So if G is outside H, then this product is also outside H. Okay, so basically we have shown a converse. So it's if and only if G is in big H, if and only if small h times small g is in big H. That is one thing. The other thing is, what can you say about two elements? Let's say H1, H2. We take two elements in the subgroup. What about H1G and H2G? So these are two sets. In fact, we could have asked a question even before. Is HG a subgroup? Is it? This also is not clear, right? For a general element small h, you don't expect this to be a subgroup. And the next question would be that if you take two elements H1 and H2, then how does H1G and H2G compare? For example, are they the same? Before that, you can ask, are their sizes the same? G was a finite group. So these are two finite subsets. Are they of equal size? What do you think? Yes, right? So H1G and H2G are always equal sized. How do you prove this? I mean, as we are assuming finite. So for a finite group G and its subgroup H containing H1 and H2, these two things are always equal. Yeah, that's a good proof. So let's construct that bijection. So an element A here should be sent where? H2 H1 inverse A, right? So the thing is that A will be of the form H1G, and when you look at the image, so H2 H1 inverse A is then equal to H2G. So this means that the map is well defined. It takes every domain element to an element in the range, right? So H1G is mapped to, for instance, H1G is mapped to H2G. Is it a bijection? How is it a bijection? So what if phi of A is equal to identity, is equal to, okay, so what you have to show is if phi of A is equal to phi of A prime. So let's not use A, let's just use H1G. So if phi of H1G is equal to phi of H1G prime, then what you have is H2 H1. So in the image, this means that H2G is equal to H2G prime, which means what? Yes, you can cancel. That's the group axiom. So which means that G is G prime. So basically, two domain elements will give the same image if and only if they were equal. So that means that phi is an injection. How do you show that it covers every element in the image? Well, that is also clear, because if you want to cover H2G, then its pre-image you can take as H1G. So this means that phi is both injective and surjective. So phi is a bijection. Right, so that means that the sizes are the same. So we don't really need the finiteness assumption, because when we started the course we said that this cardinality we will say is equal if there is a bijection, right? We didn't want to define what cardinality is, we just wanted to say how it behaves, right? So with that understanding, whether the group is finite or infinite, there is always a bijection between these two sets, H1G to H2G. That is what we have shown. For finite case, it means that the sizes are equal. Is that clear? So now another interesting thing is, which will go well with this property, what happens if H okay, something I have messed up. Okay, something drastic I have to change. Let's change it to this point of view. consider G in G, and then GH is this. Yeah, I should have taken this point of view that for the subgroup H, I will define G times H. G is an arbitrary element in the group. I hope this will not change any of the truths. So if G is in H, then yeah, G times H will be in the subgroup. If G is not in H, then it will not be in the subgroup. So I'm just using a different labeling. If G1, G2 are two different elements in the group, what about G1H and G2H? And similarly, you can ask the question whether GH is a subgroup. So what we showed here is that G1H and G2H are equal in size for any two elements G1, G2 in the group. So G1H, G2H. And so A is of the form G1H now. And G1, G2, G2, G1 inverse will then be what? G2H, G2A. G1H and some other element G1H prime. If they are equal, then what you get is G2H is equal to G2H prime and this will give you H equal to H prime. Okay, basically the GH thing I should have flipped because I want to define coset. I mean the math is correct, but that's not the presentation I want. Okay, is that fine? It was simply a mistake of copy paste. The math hasn't changed. Okay, just some labels have been changed. So the place where we are at is for a subgroup H and for arbitrary elements G1, G2 in the group G, this G1H and G2H both are subsets. They may not be groups, they may not be subgroups, but their sizes are the same. There is a bijection. Now, if I take G1 to be special, for example, I take G1 to be E, what happens? What is E times H? That is just H, right? Also, if I take G1 to be in the group, subgroup H, what is G1H? Yeah, so if G1 is not an arbitrary element in the group, but an element in the subgroup H itself, then G1H will not change. It will be same as H because it's closed under that multiplication. So that is what you learn, that actually all these G1H, G2H, their size is equal to the size of H, right? That is what I wanted to show. So for all the group elements, all group elements of G, GH is of the same size, which is the size of the subgroup H. Okay, so in the case of finite group, these are the sizes. In the case of infinite group, these are bijections. So all these GH sets, subsets are under bijection. Any questions? So now with this ready, what I can define is the collection of these things. I can define it G/H. Okay, and we will see why this slash is being used. Ultimately, this will be the same thing as Z/N. Okay, this slash is a very general concept in math. But here, let's first see whether you have understood this. So, small g times big H, these are all subsets. We are looking at a collection of subsets. So if you take the union of all those elements, the elements which you see here, how many elements will you see? Is there any element of the group G which is missing? Or is everything covered? Yes, exactly. So you understand the definition then. So let's note that the union of all these subsets is everything. Because for all G, G times E is equal to G, and your E is sitting in H. Right, so every element of big G is an element of some GH. I mean, every small g in RHS is contained in small g times big H on the LHS. And obviously, LHS is a subset of the RHS because that's where the computation is happening. So these two things are equal. Is that clear? Now these two subsets, they cover everything. Is there an intersection between them? There is an intersection. Let's check. So G1H intersection G2H is what? Can there be an element here? So suppose this contains an element A, then what happens? So this means that G1 inverse A and G2 inverse A are in H, right? It's if and only if. And this would mean what? Yeah, what can you do with this equation? This seems tricky. An easier way will be, maybe you use this. So G1 U1 is equal to G2 U2, which is equal to A. In fact, let's just call it H because it's coming from big H. So basically, A is equal to G1 H1 from the first subset, and A is equal to G2 H2 from the second subset. And from this, you can deduce that G1 inverse G2 is equal to H1 H2 inverse, which is an element in the subgroup. Okay. So basically, there is an intersection between these two subsets if G1 inverse G2, which is also same as saying G2 G1 G2 inverse, both of them are in the subgroup H. Is that clear? Sorry? They can be individually what? Right, yeah. So we are not saying anything about G1, G2 individually. But when you to look at the ratio is in the subgroup. Okay? So from this I can actually deduce, that is the punch line, that these two sets are actually equal. Do you agree? So in case there is an element common in these two subsets, then actually these two subsets are equal. Okay, they are equal because you pick any element G1 U1 in the LHS. So G1 U1 you can, okay, maybe we should see that. Mm-hmm. Yeah, maybe I can just give one more step and then the proof is right here. So what I can write is G1 inverse G2, since it is in H, you know that this times H is H, right? And now you multiply both sides by G1, what you get is G2H is equal to G1H. Is that clear? So once you show that, once you have learned that the ratio of G1, G2 is an element in the subgroup, you get that ratio times H is H, and then you can multiply both sides by G1 and you'll get that actually the two subsets are equal, right? Any questions? Two Z and 4Z, okay. You mean 2 plus Z? In the additive structure, it's 2 plus Z, 4 plus Z. Wait, let me check. I don't think that is what is happening. Yeah, those are two different subgroups. You are looking at big H1 and big H2. If you look at 2Z and 4Z, then you have two different subgroups. Here I have only one subgroup. Yeah, so you take a subgroup, I mean, okay, let's take that example since it's asked. So let's take subgroup 2Z, which is a subgroup of Z plus. Okay, so what is the specialization of this thing? What is happening? 2Z is a subgroup of Z. Let's take an element G1. What do you want to take? Just maybe 1, and G2 is 2. So what is G1H? G1H is specialized to 1 plus 2Z. And G2H is specialized to 2 plus 2Z. Right, because remember this G1 star H, but the star in this case is addition. So G1H is actually 1 plus multiples of 2, and G2H is 2 plus multiples of 2. Do you see any intersection here? You don't see any intersection, right? But suppose I have G3, which is 3. Then you have 3 plus 2Z. Now, is there any intersection amongst these 3 subsets? Yeah, so actually it so happens that G1H now intersects with G3H, but then you can learn that these are actually equal subsets. Okay, 1 plus multiples of 2 and 3 plus multiples of 2 is the same. Okay, that is what is happening. So, but since it happens at such an abstract level that it's very easy to get confused. Okay, so what we are doing above is pretty abstract algebra calculation, and what that gives you is that G1H intersection G2H is non-empty if and only if they are the same. Okay, that's what we have learned. So with all this, what we get is that that property has a name. So this is the theorem of Lagrange. We get that group G and a subgroup H implies that G by H is a partition of G into equal parts. Okay, so this G slash H that we had defined, basically subsets, special subsets of the form G small g times big H. They cover the whole group, they are of equal sized, and they are disjoint. Okay, so it's a equipartition of the group, which means what? What is the relationship between the size of H and size of G? Yeah, which means that actually the size of H divides the size of G. That's a pretty major property because you have proved it in such great abstraction. You take any group and you take any subgroup, and the size of the subgroup is a factor of the size of the group. Okay, so this is Lagrange's theorem. It doesn't use abelian properties or whatever. So a corollary of this is that the size of the partition, number of parts, is size of G by size of H. Okay, so the notation is quite nice. The slash from inside, you can take it to outside, or the bars you can take from outside to inside. Okay, that's the property. In particular, it contains the property that size of the subgroup divides size of the group. That's corollary 1. This will give you the theorem that we had left unproved, which is that for all elements in the group, the order of the group, the order of the element divides the size of the group. And hence G to the order of the group is identity, always. How do you show this? Correct, you look at the cyclic subgroup. Take H to be the cyclic subgroup of the, which is a subgroup of the big group, big G. And so Lagrange's theorem implies that G by this subgroup is equal to size of G by size of the subgroup, but size of the subgroup generated by the element small g is by definition order of the group, order of G. Right, so which in particular means that this number, I mean, it implies that it's an integer, so order of G divides the size of the group. And we have, then you immediately get that since it's big size of the group is a multiple of the order, G raised to that is identity. Is that clear? So this is a completely new, highly abstract proof of Euler's theorem and Fermat's little theorem and so on. Okay, we will not instantiate it, you can do it as an exercise. No, that we have shown, right? No. So you get G1H and suppose there is an element still missing from the big group, you pick that element G2 and you consider G2H. That's the second part. So you keep, for every element that is missing, you get a new part. They are all equal parts, they cover everything. That's the algorithm to partition your group in the nicest possible way given a subgroup. Okay? Any questions? Which group? No, G was an arbitrary group. No, you will get a part of the group. It's a recursive idea. You will reduce the big group into many smaller groups. Smaller groups have some nice properties, but that doesn't mean the original group also has the same property, because the group has many subgroups. So you can study the group, but you cannot say that the group is the subgroup. It's not the same thing. In fact, you can think about the matrix group case, the group of matrices, invertible matrices. What we have shown is obviously true, but what you are saying, all those things are false. Okay. Yeah, I want to finish this topic of coset now because we have proved the theorem we wanted. But just one more thing I can say, since we are talking about partition, that given this subgroup H or any subgroup H of an arbitrary group big G, we can define a relation which is G1 we will say is related to G2 if what should happen? Yeah, if G1 is in G2H. Okay, which is also equivalent to saying that G2 inverse G1 is an element of the subgroup H. Okay, so if this ratio is an element of the subgroup, then we say that these two elements are related. Okay, this relation is actually what is partitioning the big group. So what is the property of this relation? If you remember your relation chapter, it's an equivalence relation, right? It's an equivalence relation because of reflexive, symmetric, and transitivity. Transitivity is the thing you have to check by these two equations. And once it's an equivalence relation, you know this general theorem from that chapter that it will partition the group. So it partitions G, and these parts are what we just defined. Actually we did not call it coset. Yeah. Maybe this is the time to define that. Into the cosets. So coset is now defined in two ways, and algebraically you just write it as GH is called a coset. Okay, so coset is this special subset that we have proved so many properties of. Obviously, it is with respect to a subgroup given. So, given a subgroup H, big H of group arbitrary group big G, the coset is just pick an element small g and then multiply every element in big H with that, and that subset is called a coset. So what we have shown is that, now you can actually connect these two. You can show that the parts of the equivalence relation will be these cosets, and shown as before, this will cover the whole group. They will be disjoint, and we have also shown that they are actually of equal size. That's a special thing. Right? That is not true for equivalence relations, but this is a very special one. So here actually all these parts are equal. So these are then coset is the what we called equivalence class, right? Coset gives an equivalence class where G is one of the representatives. Okay, so you can use any of these terms, but coset is more popular in the case of group and subgroup. But in terms of relations, it's coset is basically an equivalence class under the relation defined. And what is small g? Small g is actually a representative. What are the other representatives? Small g times small h. Okay, any of these things represent the same class. Now you can go back to that silly example. So 1 plus 2z, 2 plus 2z and 3 plus 2z. The first one, the representative is 1. In the second one, the representative you can take to be 0. And in the third one, you can take representative again 1. Okay, so these are the two representative classes, 0 and 1 mod 2. Okay, so the number theoretic definitions that we gave, they were by design the same as we use in groups. Okay, so these are more general properties that we define so that in the future they make sense when you are studying more abstract objects. Any questions? Okay. So other representatives are G times H. Okay, every element in the coset is a representative of the same equivalence class. This makes sense because GH is the same as GHH. Right, whether you take small g as the representative or g times small h as a representative, they give you the same class, same coset. Is that clear? Okay. Next is let me just go into the dihedral group example. So we have defined dihedral group as the group of symmetry of polygon, right? So this was so dn was basically generated by two transformations of symmetry where R rotates the vertices of an n-gon. Okay, and S will do what? The second was it will just do the reflection. So rotates and S reflects. Along the median axis. I mean, there are many median axes. You can pick anything; it won't matter. So one of the median axes you are allowed to reflect, and the other operations are you can rotate by this 2 pi by n, right? So you rotate, basically you send the first vertex to the neighboring second vertex. So that is a single rotation. That is called r. What will be r square? So r square will be 4 pi by n, right? You do it twice, so 1 will go to 3, and so on. So there are n rotations possible, and two possibilities of reflection. Either you don't reflect or you reflect. So this is the dihedral group. So the elements look like this. It's basically, so you have r square, r to the n, and you have reflection on top. Okay, so these are the symmetries of an n-gon. So 1, 2, so this n-gon labeled by 1, 2, 3, 4, 5. What will happen if you apply r? So if we do this clockwise, then you will get 5 here, and then 1. Right, so it will rotate clockwise by 2 pi by 5. So basically 5 goes to 1, 1 goes to 2, and so on. So in the permutation cycle notation, we can write this as 1 is going to 2, 2 is going to 3, 3 is going to 4, and 5 is going to 1, right? It is this thing we are doing, single cycle of length 5. What will S do? If we do S on this, so the symmetry I want to pick is, the median axis I want to pick is this one. Okay, so if I reflect along this, then 5 will not change, and you will get 4, 1, and 3, 2. This is the action of S here. Okay, so with respect to the previous one, the middle configuration, S has the following description: 1 and 4 are getting flipped, and 2 and 3 are getting flipped, and 5 stays the same. So I can either skip 5 or I can also write 5. It's the same thing. So now there are 3 cycles, right? 2 of them are of length 2 and 1 of them is of length 1. That's the cycle decomposition of the permutation. So you can keep doing this. You can do, for example, R many times, and then after that combine with an S or skip S. So this is called the dihedral group of symmetry of an n-gon. Any questions? Okay, so maybe you can do the coset example here. So what will be the size of dn slash r? Right, so the group generated by the rotations, what are the cosets? How many are they? You can show there are 2, right? And what are the cosets of the group generated by the reflections? That will be n, right? Yeah, so this is intuitive, but you should actually prove this. So one way to prove it is that you show that the representatives or the the representatives are basically given by dn and sdn. This is what you have to show, that there are only 2 cosets, representatives I can pick to be just identity and s. And here the representatives are r to the I. Okay, so these representatives will be n many. These are the n rotations. Right, so in symmetry you can see nicely what this kind of this mod subgroup is doing. Right, the mod subgroup helps you understand the bigger group, and you can see that many things are false. So these 2 subgroups, both of them are cyclic, but the dihedral group is not cyclic. Right, dihedral group requires 2 generators. You can't do it with 1. That also actually you have to do as an exercise. It's not, may not be immediate. So what you can show is, you can show an identity. I mean, actually, already from the first case, you can show that when you, on the second coset, if you multiply by r, what happens? What is Rs? You can use the definition and actually drop picture and conclude that Rs will be equal to SR inverse. Okay, this is the relationship. So which is also the same as RSR is equal to S, or S inverse RS is R inverse. Okay, so these are all saying the same thing. And what this means is that there is a relationship between reflection and the rotation and reflection, but it is not very straightforward. Okay, you have to do the operation 3 times. Like first you rotate, then you reflect, then you rotate, and then it will be equal to reflection. Okay, there is no easy relationship. This is what follows from also these coset structures, and it means that the group is not cyclic. So the last topic I wanted to do, which I don't think will be possible now, is to count necklaces. So here the problem is that you have this same polygon, and you want to, so the vertices are basically beads. The beads will be colored. So the beads which are colored red, they look the same. The ones which are yellow, they look the same. But of course, across they look different. Right? So they are identical beads, but once you color them, they look different because of the color. So this polygon will be called a necklace, and under the symmetry, if there is a transformation, then they will be called the same necklace. Okay, so this needs an example. So we want to count the distinct necklaces of 4 beads with 2 colors. That's the basic question we are interested in, with the following understanding that suppose, so 4 beads means that it's basically a foregone rectangle or a square. So let's color them black and white. So you have black, white, black, white, or you can have white, black in this order. So are these two the same necklace? Why is that? Because if you apply R, then the first one becomes equal to second, right? So we basically want to count the necklaces modulo the symmetry. Okay, so if two things can be transformed from first to the second, then we call them the same. So we are interested in counting how many distinct necklaces are there, which means that give me a set of representatives such that from one I cannot go to anything else under the action of D4. Okay, the dihedral group symmetry. So these are the same, but what if I have this one? Is it the same? So this is different, right? So first two are the same, third is different under D4 symmetry. So 1 and 2 same under Dn, under D4, third is different. Right, so if we use 2 blacks and 2 whites, then you only have 2 different necklaces. You can show that in this simple example. Yeah, so that is one thing. One case, we have used 2 blacks and 2 whites, but we could also have done no black or 1 black or 3 black or 4 black, right? What happens then? And you can pick this median axis to be this. So you can rotate 4 times, or you can reflect once along the median axis. Okay, but even under that, you can see that the third one is different, right? That's the full D4 group. Okay, so this is the median axis, so this is the same as this. And so on. So how many necklaces for 0 black? Just one, right? How many for 1 black beads? That's also one. 2 black beads, we have counted 3 black beads. And 4 black beads. So this basically means that then the total is 2 plus 4, 6, right? So number of distinct necklaces under the action of D4 under this symmetry is 6. This is the answer. So without D4 it would have been what? If we were not caring about any symmetry, if everything looked distinct, yeah, then it will be 2 to the 4. Right, so there is a wide gap between 16 and 6. Right, so you have seen 2 raised to 4 is a simple count, but then as soon as there is a group action, then the count becomes complicated, and it breaks up in particular into many cases. So that case study you have to do somehow systematically. So as the number of beads and number of colors increases, this calculation, this count is a complicated process. So that is what was supposed to be the last topic, but we'll skip it. If you are interested, you can read about, do you know the topic? It's called Burnside's lemma. Or orbit counting. So if you are interested, you can read that. But Burnside lemma basically is a property of this group action, like the DN group action on a necklace, which uses C colors and N beads. And what it does is that it counts the orbits. Okay, so the DN group action on this, how many distinct orbits there are. So an orbit is basically you take one necklace and you apply DN action on it. So all the necklaces which you will get, they form an orbit. Right, so they are considered one. Then you look at some other necklace which is not in this orbit, look at the orbit of that and so on. So how many such orbits are there? That is what we are interested in. But I think it will be too much to try to pack it now. So that is left as a reading exercise. Any questions till now? Okay, so what you can read is so this and so basically Burnside lemma. And second thing you can read extra is normal subgroups. The reading exercise, let's hope not. That will be too much to do without being taught in class. So if you are lucky, I won't give any questions. Unless I find very simple solutions, then you have to find them without using Burnside lemma. Yeah, but this lemma proof, etc., and application we will not be doing. I mean, it's a pretty mechanical thing. Once you have seen the lemma, it's a mechanical calculation, so you can see the mechanical calculation. It's not very important for the exam. It is just a systematic way of doing what we did here by hand. But already if the number of beads is 6 and colors are 3, this already explodes into cases. So how do you make those cases systematic is the point of one-side lemma. And the other thing which is immediately needed in groups is subgroups which are normal, because then this G/H, this set, this itself becomes a group. Okay, so you can construct from the equivalence classes another group. That will complete the recursion idea. You will understand the subgroups and you will understand the set of cosets also as a group. You will have two different groups, which will not be a subgroup. Right? G/H is a complicated thing. So it will be a new group operation basically that can be defined. So these are the things you can study as extra topics. Let's stop at that.